Okay, class. Today we'll look at problem for failure analysis, and we'll have dogbone-shaped specimen. We will examine the specimen from three perspectives: static failure analysis, fatigue analysis, and buckling analysis. Okay, the geometry is provided here, and on top of it we applied a pressure with a magnitude of 50 megapascal, and the bottom is fixed. Okay, we'll start from Workbench, where we'll create static structure project. Okay, let's create one static structure. And the engineering data, the material will use the structural steel, so we don't need to create it. It's a by default material. And geometry, double click on geometry, where we will launch geometry. We will create the dog bone specimen. Here we are, we have space claim open, and then we'll right click, select the new sketch plane. We use XY plane, click on it, plane view. So we're before doing that, we'll set up the unit. For the unit, you'll see that one dimension is 15, and we'll draw half of it. So we want our unit, the minor grid is 0.5 millimeter. So the unit is millimeter. The minor grid will use 0.5 millimeter. Okay, let's start to draw this geometry. So click on line, and then I will use Cartesian dimension to help us draw it. So what I do is I will start from center, and where I will go up by 19, because half of it is 19. So I'll go up 19, and this side I will go, waist side will go to 7.5, 19 and 7.5. Okay, start from here and go all the way to 15 millimeter, and go down by 9 millimeter, 8 millimeter, and then go all the way here and then go up. Okay, and then I will draw the narrow part. I still use Cartesian dimension. We'll start from here, go all the way up, and then this is 2.5. We'll start from here and go down 11 millimeter. Okay, and then I will do the same thing to draw another part. Escape, Cartesian, start from center, go up 11, and then 2.5. And then I will draw down. Okay. Alright, and then I will cut this part away. Now I have the upper half of dog bone geometry, and we'll use mirror to copy the upper half to bottom half. So click on mirror, and then I will use X as a mirror, and I'll select all the geometry I have drawn. Now we have it. Okay, this is 2D geometry. I move it up, and then we'll use a round corner, 3 millimeter, round, another round corner, 3 millimeter, and then round corner, 3 millimeter, the last one, 3 millimeter. Okay, now this is the finished 2D geometry, and then I will use pull. And the thickness is, or draw it up as a 0.75. Okay. Now we have this geometry. Everything looks good, and then we'll exit from space claim, and then we'll go to next step. Go to the modeler, where we'll first do a static failure analysis. Static failure analysis means that we'll check the stress distribution and see whether the stress reached the yield strength. If its yield exceeds the yield strength, means there would be a plastic deformation, and the material will experience permanent damage or a shape change. Right, now we are in a mechanical modeler, where first thing is we will mesh the material. Again, the default material structure is steel, so we don't need to assign material to it. We directly go to mesh. Okay, click on mesh, and then to make it simple, I will go directly to the element size. I will assign 0.5 millimeter and then mesh it. Right click, generate mesh. Okay, the mesh looks good. So if you look at the mesh, this looks good. And then right click, assign bottom condition. I will fix the most bottom part. Click apply and fix the bottom, and I will apply pressure on top of it. Pressure, top surface, apply, and the magnitude is 50 megapascal. Right, and then with that, no selection, try it again, apply. Okay, 50 megapascal, looks good. And then solution, we'll look at deformation, and then we'll look at equivalent stress, and then we'll do the calculation, solve it. And you will see that the stress distribution. And well, if you can see the maximum stress is around 216. And if you look at structural material, go to material structures, material, you will see that its tensile yield strength is 250 megapascal. That means in terms of static failure, and the material we applied and the stress we applied is safe. Okay, to better illustrate this point, what you can do is we can look at a new tool. So here we can insert like stress tool, maximum equivalent stress, and you can look at the safety factor, evaluate all result. And you will see that the safety factor, when the safety factor is larger than 1, that means is statically safe. There is no static failure. So you will see that then the lowest safety factor is 1.15. So it's relatively safe, and the safety factor tell you that where you will. If the smaller the safety factor, that means you have more risk at that point. All right, and we finished the static failure analysis. Next one, we will work on the fatigue analysis. For the fatigue analysis, what we can do is we'll go to solution, and we'll insert fatigue analysis, fatigue tools. And here's the fatigue tool. And the fatigue tool, what we can do is we can do a for reversed loading, the material, time domain, definition. Let's see that. For the mean stress theory, remember in class we have learned Goodman, Soderberg, Gerber, and you can choose one for fatigue analysis. Here we can choose Goodman fatigue theory. Okay, after that, we can look at, we can insert the life analysis. So this will help us create the SN curve. So under life analysis, what we can do is we can input safety factor. So for safety factor, you can assign that how many cycles you want to run. Here we can run to 1 million, so 6 zeros. And then now we finish this, and we will evaluate all the result. And you will see that the safety factor, and that's the life analysis, that you will see if we use 15 megapascal for the loading, so cyclic loading, and the live prediction for this material at different location, and also if we use 1 million cycles as an indicator and the safety factor for different areas. Okay, this finished the fatigue life analysis, and then we'll exit from static and fatigue analysis, and we'll do the final analysis, is a buckling failure analysis. To do that is you can go to the result, right click on the result of the project schematic for the static structural analysis and transfer data to new. Okay, doesn't work. Go to solution, not result. Okay, go to the solution and then transfer data to new eigenvalue buckling analysis. Okay, and then we will have an eigenvalue buckling flowchart diagram, and then we'll go to the setup. We'll set up the eigenvalue buckling failure analysis. So it's quite easy for buckling analysis. What we need to do is we want let the modeler know that how many modes we want to do. And there are different buckling mode. Like it's very similar to the vibration, that you have different vibration mode, and for buckling there are different buckling mode. Okay, here we go to analysis, and here we can change the buckling mode. Let's say we use 3 buckling mode, and after that we go to solution and we input deformation, and for each deformation we can associate with the 3 mode, each of the 3 mode. Okay, I insert second total deformation, second one will associate with mode 2, and then insert the last one, I will associate the mode to 3. After that we can do the calculation. Okay, calculation finished. So we have 3 buckling mode. I can click on it. You will see that this is the first buckling mode. If you look at the animation, you will see that how it buckles. So this is the stability. So when you apply pressure on top of it, when the pressure too large, it can buckle. Okay. okay, so there's one thing I want to change. I forget changes for solver control. Include negative load modifier. I will select as no because I don't want to change the load. So I will set as no, and then we'll do the calculation again. So we only apply the load that 15 megapascal. We don't want to change it. There's no reversing load to apply on it. Okay, and then let's look at it again. Well, that's the 3 buckling mode. And there's a first buckling mode, second buckling mode. You'll see that the buckling is different. This third buckling mode. And the thing is to tell you that whether there's buckling or not is to look at the load multiplier on the left corner. So if you look at the total, the first mode, and the load multiplier is smaller than 1, that means the load is too large. There will be a buckling, the first mode buckling. And to avoid this, the first mode buckling, you need to use this number times 15 megapascal. The pressure applied must be smaller than that. And then there's no first mode buckling. And you will see that second load multiplier is 2, third one is 5.7. That means there's no second and third buckling mode occur. But there will be a first mode buckling because the load multiplier is smaller than 1. Okay, well, that will finish today's lecture, and we'll stop here.